Hi guys, welcome back. So in this video, we are gonna learn complex numbers method to solve any AC circuits. So watch till the end, you will gonna learn something new concept here. So alright guys, let's continue. So before we solve AC circuits, first we'll learn basics of the complex number. So yeah, we represent in organ plane. So this is a real axis and this is imaginary axis. So we represent a complex number equal x plus iy. So both x and y, here x is real part and this is imaginary part. So iota we can write as root of -1, as you know. And so as we rotate a complex number by pi by 2 degrees, so we have to multiply it by iota. So we are multiplying with iota always by rotating pi by 2 degrees. So here we multiply iota again and I cube times z. So this is called a real axis and this is imaginary axis because here we have iota here. So we will see some properties. So we can add two complex numbers. We can add and subtract basically. So z equals z1 plus or minus z2, but we can't add mods directly. So and in multiplication and division property, we can multiply and divide the mods directly. Okay, and so we will see some argument properties as well. So z equals to x plus iy. So in this argument of z equals y by x, so the argument t is basically the phase angle or so angle between two complex numbers. So tan inverse y by x. So in when if x comma y greater than 0, we write y by x, and here we have two properties of complex numbers in arguments. So argument of z1 times z2 equals argument of z1 plus z2, and argument of z1 upon z2 equals argument of z1 minus argument of z2. So similar to log properties. So now we go to AC concept, and so as we represent resistance in x-axis and XL in positive y-axis and X in negative y-axis. So in the complex number concept, we have to multiply XL with iota and XC with minus iota. So by this, this converts into DC. So we can directly solve it by current electricity topic. It is easier. Okay. So why we have to multiply iota and minus iota as we analyze in the situation. Okay, iota and minus iota. So similar to this. Okay. So and we have to know one concept here. So basically resistance and current and voltage are in same phase always. Okay. So the phase angle between them is 0 always. Okay. So now we analyze some AC circuits. So we have to write voltage equals to E naught sine omega t plus phi. Phi is phase angle between them. All right. And first we analyze purely resistive circuit. Okay, we basically write I equals V by R. So from this, okay, the phase angle between voltage and resistance is 0 as we know. So I written phi equals to 0 and directly wrote V by R sine omega t. So now we write for capacitive circuit. So I equal to V by XC. Impedance is XC here. So XC lags minus pi by 2 with current. So as you know, okay. So the phase angle of XC is minus pi by 2 and phase angle of voltage is 0. So argument of 0 upon argument of minus pi by 2 is 0 minus of minus pi by 2 got plus pi by 2. So from this we can analyze it. Current leads the capacitance by 90 degrees. So why? Because we got here positive 90 degrees. And for inductive circuit, I equals to V upon XL. So XL leads current up by pi by 2 degrees. So voltage phase angle is 0. So the phase angle of current is 0 by pi by 2. So from this we get minus pi by 2. So I equals V by XL sine omega t minus pi by 2. So from minus pi by 2 we can analyze that current lags inductance by minus by pi by 2 degrees. Okay. So for next we see for RLC circuit. So this is important. Okay. So I have to 3 in series and one AC source. Yeah. Okay. And we convert this into DC circuit by by using complex numbers. So we multiply I with XL and minus I with XC. So this is converted into DC. Now we add R equivalent or Z equals to R plus I times XL minus I times XC. So these are equivalent here. So if we take mod of this, we get impedance equals to root of R square plus XL minus XC whole square. Okay. So yeah, now we do example problem on this. So I have took this problem from Pathfinder. Okay, so this is a easy problem, Okay, let's read the problem. So we have a circuit shown consists of two identical coils, each of inductance L, two identical capacitors, each of capacitance C, and a variable frequency alternating source. Find expression for the angular frequency of the source at which peak voltage between A and B terminals becomes eta times of the peak voltage of the source. So basically in the question they have said that the voltage between A and B equals to the peak voltage of the source. Yeah. Now we solve this problem. Yeah. Okay. I converted basically this into DC circuit by using complex numbers. I multiplied iota and minus iota with capacitive and inductance reactance. So, okay. In the question they have said that VAB equals eta times V. Okay. Now we write for voltage at V, voltage at A point. So both three are in parallel series, parallel. So the voltage is same across them. So here we take 0 volts. Okay. So now we write voltage at A point. Okay. IRMS into the capacitor reactance. Okay. And so IRMS here is V by total impedance XL minus XC mod into I. So here I took mod by because we don't know any value. So into the capacitor reactance minus I into XC, equation 1. So similar to B point also, I into inductance reactance V upon XL minus XC mod into I into XL, equation 2. So we take the difference of both. VAB equals V times mod of XL minus XC into I into XL plus XC into I. So here I terms get cancelled. As we know, XL equal to 1 by omega C and XL equal to L omega. So here we take the ratio of these both VAB upon V. As we know, VAB upon V equals eta. So as we substitute the values of this here, we get two values by opening the mod plus minus. So we get the value of angular frequency in terms of eta equals 1 by root LC into eta minus 1 by eta plus 1 comma root of 1 by LC into eta plus 1 upon eta minus 1. So this is a complex method. So if you get any doubt, the comment below in the comment box, guys. So if you like the video, do subscribe and share, guys. Yeah, thanks for watching.